minutes ago. You can bring a note card, both sides of a 3x5.
Woo-woo.
No worked examples, but you can put theorems, definitions, and procedures. You can't have a bunch of worked examples for how to use the theorems. But you can have the theorems, totally fine.
As in like the names of theorems and whatnot?
Yeah, you can put all that stuff on there. Just can't have worked examples.
Worked examples.
So what's the line between a worked example and a theorem? Like if the theorem...
Theorem, like you could write the divergence theorem, but you can't have like, oh, if the vector field is x comma y squared, you can't have it worked out, but you can have the theorem itself.
Okay.
So you can have the double integral of f dot n ds is equal to the triple integral of divergence.
And procedures are like to find critical points, find f sub
Yes.
x, f sub y, set them equals 0. Like, so you
Yes.
can have like steps written down.
Right.
You just can't have a specific.
That's a good example.
with
So if you're trying to find critical points, you can describe how to find them.
Like if we have to use we have to put something in there, just like a general x squared or something. Like, is that okay? Like.
Yeah, you could generalize it.
Okay.
Yeah, you could generalize it. Will?
Are we allowed to run an electron microscope?
Yes. You have to leave it behind though once you leave.
Wait, what?
For the questions from previous exams, is it just like questions from those chapters we should have to study, or is it like questions off of
I will,
the exam?
literally, it's a copy paste and edit. Copy paste and edit. Numbers will be different. Numbers will be different. But they will be, but the wording will be identical. All the wording is the same. So 3 from each of those exams and then 6 from chapters 14. Yeah.
Can we bring a magnifying glass without you confiscating it?
Bring what?
A magnifying glass?
That doesn't give you, that's not valuable enough.
Talking about getting previous tests.
That's valuable enough.
That's good.
How is that going to help you? That's like
Okay, so any questions, overall questions, summary questions?
I want to make a sweatshirt.
I got it. Yeah, good. Yeah, question.
Number one
Number 1
from exam 3.
from exam 3.
That's
That
the
was the
easiest.
No.
That was the easiest.
Right, that was the ED.
No, but it wasn't solved.
I know, that one's not going to be on there.
Number practice number 1.
Will.
Are we allowed to bring an origami?
Oh, gosh! I love origami.
There we go.
Bring me an origami Yoda this big.
Alright, can we bring an origami index card?
Diana.
So you're saying from the first 3 exams it'll be the same as like what you have on those exams, just one of the questions on there. Should we focus on like the problems that like conceptualize the chapters the best?
volume of pi.
I would.
Just like,
I would.
because obviously
yeah.
like studying like long chapter, your
Let-
number 3 exam, like you don't care about the first question, but like
Oh, I
look
saw
at those harder concepts.
Yeah, I think that's a good idea. I mean, I'm not going to give you the longest and hardest ones because that's just too much work.
So like not the center of mass one?
So not the center of mass one, for
Okay.
example.
Yay.
I've been practicing that
Not
so
that
much.
big. Not that big.
The center of mass one.
I cannot get the answer that you got.
be a study session?
I can show you one. I should show me, yeah.
This
I
one.
can't get it.
Oh,
Center of mass.
Oh, is it the cube?
it's the
Yay.
4 cube?
I would like.
But it's gotta be big.
I like it. No, recognize your siblings.
yeah.
It'll be
Guys follow
the
National Geographic
short
on
one.
Snapchat?
I don't have to know that. I'm too old for that.
You gotta watch this. It's a deep sea eel.
A deep sea eel.
Deep sea eel.
Wait, it's about 5
There it goes.
Is it upside
It
down?
is, sorry, it's upside down. This is like the only thing I watch on Snapchat.
Oh, I did?
Yeah.
Oh, we
Plenty of them.
will you just email me a reminder because I'll still have it in my inbox.
Yeah.
So,
There's a video game with an
yeah,
eel in
yeah,
it.
sorry about that.
Oh,
I think I probably looked at it separately from when I.
Feels creepy.
This one's, that's, yeah, it's
look at it. Look at how
Let us
it's really little though.
get niggas card day by day.
Yeah.
spinning cube is ours.
That was its mouth. So you just rolls up that
And then it like turned into
Then they have like a whole article on it.
Did anybody find a calculator in this room?
It's black, kind of like this one. It's a
Yeah.
TI-6.
So go check with the math administrative assistant right around the corner in the math
Or Steve
office.
Wolf. He's been here right before we are.
Or Steve Wolf, yeah. So, yeah, go check with the administrative assistant first, and if not, see if Steve is in 1305.
1305. Got
Yeah.
it. Thank you.
Yeah, you bet. All right, so first question is 14.6, number 12. Is there other ones you want to go over from chapter 14?
Oh, I had those ones up on the board the other day. but I can't remember which ones they are.
Oh,
So
number
let's-
6, 14.7?
6 and 14.7?
I think that was it.
I think that was one of them, but you had one from 14 as well.
All right, so let's start then with the 14.6, 12.
Okay.
14, 6, 12.
Oh, the heat flow guy? It's for you, Grant.
I may, yes.
Is there a specific issue with this one, or just sort of the?
Oh,
it's long?
It's really long, yeah.
Just yes.
DS, is that what you said?
Just yes.
Just yes.
Guess. Oh.
Okay, so we have a vector field that we are going to create right here called capital F, and it's going to come from this function t. So that function is going to essentially be like a potential function. So let's first find the vector field. So capital F is going to be negative k times the gradient of this. So the gradient of t is going to be the partial with respect to x, which is going to be negative 130 e to the negative x minus y, comma, partial with respect to y. Same thing. And then the z component's just 0. So our vector field is going to be minus k times this. And what do we want to do here? We want to compute the outward flux. So to compute the outward flux and across the surface, let's see, where's our surface down here? It's going to be a cube. So we will use the divergence theorem. Obviously, we could parameterize all 6 faces, but that's a lot of work. 99% of the time when you have a cube or something that has lots of faces, that's the whole point of using the theorem, is that it chops off all that extra labor. So we're going to think about this as a cube, and the length of each side is 6. So we have a 6 by 6 by 6 cube. So let's go with that. So we will have to find the divergence of this vector field. And I didn't write down the extra piece of the vector field yet. So capital F is just negative k times this. So that negative k, if we want, we could distribute it into the vector and put it in front of each. So let's just go ahead and do that. So we're going to have 130k e to the minus x minus y, comma 130k, and I didn't write the k there, I will in a second, and then 0.
But K is just 1.
Oh, K is 1?
Up there.
Oh, right there. I didn't
Yeah.
see that piece. Oh.
Then what's the point of K?
Yeah.
Wait a
yeah,
second.
exactly.
Wait a second.
Yeah.
Hold on, so K.
Wait a second. But there's a negative in the field. F equals negative k del c.
Right, so it's
Because
negative K, so
-1.
that's going to
So
be
it
a
just takes
negative
away the
1 being
negatives.
multiplied through.
Got it.
Right.
Yahtzee.
Oh, pretty cool.
Yeah.
Why is T negative?
So they give us that F is negative K times del T. If K is 1, then we're going to take negative 1 and multiply it by del T to get F.
Right, but why is del T negative?
Why is it negative?
Because it says
Because
so.
the partial derivative with respect to x, we have to use the
Duh,
chain
right.
rule. Chain rule! All right, so the divergence partial of each component with respect to either x or y. So partial of this with respect to x is going to be negative 130 e to the minus x minus y. How about the partial of this one with respect to y? Same. So we add those together and get, what would our coefficient then be? 260. So that will be our divergence. So then we're going to integrate that throughout the solid object. So we integrate this, and our solid object has limits -3 to 3 on all integrals. -260 e to the negative. So dz, dy, dx. Order doesn't really matter there. There's no z, so we're just going to multiply by 6. So we'll integrate this with respect to y. When we multiply that by 6, we are going to get 1200 plus 1560. Double check that I multiplied by 6 properly. So we're going to integrate with respect to y, so that's going to give us a negative, which I'm going to make the positive out in front then. And we're going to have, when we integrate, we're just going to end up with the e to the negative x negative y. And that's -3 dx. Any questions on that so far?
How did you get the 1560 to be positive real quick?
So when we integrate this e to the negative xy, e to the negative x negative y with respect to y, we have to divide by -1.
Got it.
Did you multiply by 6?
Yep.
Okay.
Yep, 1200 plus 360. And then we are going to plug in our 3 and our -3 over here.
Wait, where does the positive come from exactly again? Did I miss that?
Yep. Give me 1 second. So we're plugging this in for y, so we're going to get e to the -x -3 minus e to the -x plus 3 dx. And Will, your question was, how did that become positive?
Yeah.
So we are integrating with respect to y. There's a coefficient of -1. Chain rule says we divide by -1, so that's going to offset that sign.
All right, yeah, you just skipped the z thing, so I got tad confused.
So the z thing is, there's no z, so we multiply by 6.
Yeah, that's what I figured. I just couldn't figure out how we got from multiplying negative by +6 to
Make it positive. Okay, so now we just integrate with respect to x. We have a function of just x, so that's pretty straightforward. We're going to end up with 1560 multiplied by, integral of that is going to be itself divided by -1, so negative e to the negative x minus 3. And then this will be positive e to the negative x plus 3, and that will be -3 to 3. So then we have 1560.
Isn't that 0?
Now, we're integrating with respect to x, and there's an x in each of those.
You can't just add these together.
Okay.
Yeah, these don't have the same exponent. You can only add powers if they,
oh, minus and plus.
right. Yeah.
Simplify it down.
We can't combine those yet.
They're tiny.
Okay, so plugging in +3 up here is going to give us negative e to the -6 plus 1. And then we subtract off what happens at -3, so we get plus 1, and then minus an e to the -6. So we get all that. That cannot be simplified too much. We can factor out a 2, and we would get 3,120. And then minus e to the -6 plus 1.
So you just come, okay, got an answer.
So
Yeah.
factor out the 2.
What?
Does that look good?
Why is it e to the -6 for the second one? Wouldn't it be e
Right
to the
here.
+6?
So we're plugging in. Yes, thank you.
So that can't be
correct.
combined.
Yep. Can't do that. Good point. Thank you. +6. We're plugging in the -3 right there. So the negative sign's going to go in front, but yeah, absolutely. Good eye. So this we can't simplify much more than. This is about as good as it's going to get. We're going to have 2 minus e to the -6 minus e to the +6. Yes. And we can't combine those. So. Okay, that's 14.6 problem. Grant?
The reason I was stuck on this one is because my math lab, in its overflowing wisdom, decided to take the approach where it parameterizes all 6 faces of the cube.
Oh!
Yeah.
It forces you.
Yeah, I wouldn't. That's not
never
how you
look-
would. Yeah, you won't want to do that. I won't make you do that on the test. The whole point of the theorem is that if you have a solid object with multiple faces, you can avoid that. That's the whole point of the theorem.
All right.
And so pretty much this is we just obtained the flux of the cube.
Right, so that's a positive number. So that means, I assume that's a positive number.
Multiply by 2 negatives.
You know, we would have to double check for sure. But, oh no, I guess that's a negative number. So what does that mean then?
It's
It's going in the opposite direction.
So it means that there's stuff coming in. They call that a sink because it's pulling.
because outward
Alright,
flux
so-
is positive.
Outward flux is positive.
So F is pretty much the direction of the vectors at any given point, and then we got the cube for the limits of the integrals to find the cube.
That's right.
Yeah, that's a negative number.
Negative number, so flux is going, so the flow is going to be in instead of out. In instead of out. So 14.7, somebody wanted number 6. 14.7, 6.
You know, one thing we need to do is find a platform that lets the teachers write their own questions.
Yeah, you can't, in my math lab, you actually, they have set it up so they have now have it set up semi-recently where you can actually modify existing questions, but it's kind of a hassle. But you can do that now.
They just don't
Okay,
make it easy.
yeah, it's a lot of work though. Okay, so this says evaluate the line integral in Stokes' theorem. Assume that n points in the upward direction, and there's our field and there's our surface. So the surface is an ellipsoid, and we want to use the line integral in Stokes' theorem instead of the double integral. So the double integral, you would integrate the curl across the surface, the normal component of the curl, or we can go with the line integral. We're just dealing with the upper half of this ellipsoid. So we've taken an ellipsoid, we've chopped it in half, and the boundary is, that curve. So let's take a look at this. So the upper half of this ellipsoid, so if we want the upper half of this ellipsoid, we're going to be thinking about the intersection with the xy plane. That'll give us the curve that we're going to integrate around, and that's going to be...
That's an ellipse.
That's that's an ellipse. Just a standard ellipse. So y is going to be the bigger one. So there's x, there's y. So the ellipsoid, the half of we have a semi-ellipsoid, and that's going to be pointing out of the board.
Hemi-ellipsoid.
Hemi-ellipsoid. Well, I guess we would call it a hemi-ellipsoid.
Because you call it hemisphere.
It's a hemisoid.
Yeah.
Hemisoid.
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 Okay, so now what direction should we have the orientation of this curve go? Counterclockwise. So it says that we want upward normals. So if we have our dome here and we want upward normals, that means we're going to go counterclockwise as we're looking down. So this would be this direction. Great. Everyone okay with that? So if we're going to use the line integral in Stokes' theorem, we need to parameterize the curve. So, bless you. So what will our parameterization for the curve be?
It's going to be 2
Cosine
2 cosine t.
6 sine
6 sine t.
0.
0.
0. Is that good for everybody? So if you're not 100% sure, you just use the Pythagorean theorem, sine squared plus cosine squared is 1. Here we have that x is equal to 2 cosine t, so cosine of t is x over 2. Y over 6 is going to be sine, and then you square it and get 1. Yeah?
Is z 0 because we're in the xy plane?
Yes. So on this curve, z is 0. Right? That curve, that half of an ellipsoid is touching the xy plane, so the curve is in the xy plane. So the z value for the curve is 0.
So yeah, how come we're only doing the xy plane again?
Because they tell us to look at just the upper half of the ellipsoid.
Okay.
So they tell us to just consider the upper half, and so that means that the boundary curve is on the xy plane, right? Do you agree?
Oh, so that RT is for the boundary curve.
Yes.
Okay.
Yeah. Yeah. This is that curve right here. That's the interesting thing about Stokes' theorem. There was one of those problems in the book that said something about the surface integral. Is it changed or maximized or minimized for what value of letter A? And the interesting thing is that, well, with Stokes' theorem, it doesn't matter how big this ellipsoid is over here. If it has this boundary curve, that doesn't affect the value of the line integral. So that constant in that problem doesn't affect anything. Okay, so the line integral, so we're going to do FDR, which there's so many ways to write this. Maybe I should write it since we're reviewing. The most basic, the introductory way to write it is like this, with a capital T around the curve C. But that's only useful if you parameterize according to arc length. That's usually not the case, so we kind of ignore that and go with FDR. Even if you were parameterizing according to arc length, this still would work out just fine here. You don't have to memorize that one. So for a line integral, we do that. And then the evaluation theorem says to do this on the interval a to b. So those are the three steps of a traditional line integral, or a circulation integral, or a work integral. All those are the same. Circulation, work, and when someone says line integral, that's what they mean. Okay. So we take our vector field, we plug our parameterization into the vector field, and then dot it with r prime. So let's get our vector field right there. This is just the sort of traditional radial vector field, x, y, z. So our parameterization is going to go 0 to 2 pi. And we dot f, so f really is just this, correct? Yeah.
I'm sorry, you said that divergence, not divergence, Stokes, curl, and circulation, or, I'm sorry. Oh no.
Circulation, work, and when people say line integral, 99% of the time this is what they mean.
Okay, so those are all equivalent.
But we've seen a different line integral for flux, where we put, instead of dr, we put dr perp. But when someone says evaluate the line integral, 99% of the time they mean a circulation integral or a work integral, like that.
Yeah, I thought I saw something about an in above, like as in a normal vector, just upward of the slide. Did I? Yeah, I didn't read it very carefully, but.
Yes, that's why the orientation is counterclockwise, because we're choosing outward normals.
Okay.
For that. So
I don't know what's going on with this unit.
So we're dotting f with r prime. So here's f essentially, correct? Because f is just x, y, z.
Isn't the question asking us to dot del dot f with them?
I don't. This
or del cross.
It's a double integral.
So this right. Yeah. Thank you for pointing that out. This is curl f. That's curl f, and this is the general way that we evaluate a line integral. In this particular case, the vector field is really a different vector field called curl. Right? Curl is an example of a vector field, but I just did say dot f with r prime, and by f in this case, we do mean curl, so we should find the curl before we do our dotting. Yeah.
Wait, hold on. But that's a double integral.
So you're just doing the single, right?
You're just doing the single.
Oh, yeah.
So,
okay, thank you. All right, so. Okay.
I quit.
Yeah.
I quit.
Yeah. Good, great. Yeah. So 2 things. The double integral is over the inside. The double integral over the inside, when you do the double integral over the inside, you're integrating curl f. So if we were going to evaluate the double integral directly, we would find curl. But they are saying don't use the double integral, use the single integral. The single integral around the outside is the circulation integral. And so we don't take the curl to do the circulation around the outside. This takes care of, this takes us around the outside. That right there, the T, is the equivalent of curl because it's taking the tangential components, all right, around the outside. So the curl is what creates, the curl on the inside creates the circulation on the outside, and grabbing all the tangential components of the field, which is what f dot t does, that gives us the line integral around the outside. Yeah. Okay, so this is f in this case. This is f. because f is just x, y, z. So we dot that with that. We get minus 4 sine cosine. And then we get plus 36 sine cosine. Yeah, there's a lot going on.
That's just you said, right?
And that will be, we can do it 2 ways. We could either do u sub or we could convert it to a double angle for sine. So that's going to be 32.
I don't like that.
Okay, so if we integrate that with respect to u sub, this is u, this is du, and we would just get u squared over 2. So that's probably the simplest way.
U squared over 16.
You scared?
When we integrate this part, we get u squared over 2, and then there's the coefficient,
So we get
which we'll
16
get
sine squared.
multiplied by, so we're going to get 16 sine squared of t, and that will go 0 to 2 pi. Oh, yes. I heard somebody say 0.
We could have changed our limits when we did u, and just stopped.
Okay, what's that? Question?
So I remember you saying like vaguely that the if it tells us to find the double, that we need to actually do the single. That's
So listen carefully to this.
okay.
So this now here they've said it very explicitly. They've said use the line integral.
Do the line integral.
But usually what they will say is use Stokes' theorem to evaluate this. And that will mean to do the line integral. If they say use Stokes' theorem to evaluate this,
They mean you.
then they will mean to do the double integral.
How are you going to say it on the exam?
I am going to say it.
Like the book or
He
like
has
your
to
own?
Oh, I don't have it right there.
Dang it.
I will try to make it as explicit as possible which side to use. Use the line integral side of Stokes' theorem to find.
So you're going to tell us like use, and that doesn't mean use the double. That
Yeah,
means
that,
use the
yeah,
single.
yeah, that's just the way the book sometimes, that's the way a lot of books do it. When they say use the theorem to evaluate the double, they mean, well, go to the single. And if they say use the theorem to evaluate the single, they mean go to the double. I'll say it more like this. This is very explicit. Evaluate the line integral.
That's the single one?
That's the single one.
Okay.
Line integral is the single, and surface integral is the double.
All right.
If I don't feel like it's explicit enough on the exam, can I ask you and be like, are you meaning double or are you meaning
Yes.
single? But if it's like that, I mean, obviously it's.
That's all. I'll go back and double check
Yeah.
and make it explicit like that. Just to be safe. Yeah. That's not the part. That shouldn't be the hard part.
Can't you just,
Is reading.
What?
you should just put out evaluate Franklin D. Roosevelt.
Yeah.
I think he was a fine president.
He was a fine.
Kathy has a question.
Kathy who? Yes. Scott.
So if you're doing the surface integral and you have the curl f dot n, if you get 0 for your curl, can you just say that it's 0? Do you have to do any more work for it?
Nope, you're done.
Okay. Not like he's gonna do that on the exam, so it doesn't really
So
matter.
yeah, if you have this curl f. I need water. So if we get this and if you have the curl being the 0 vector, then you can just immediately just do that.
Okay.
Yeah. That's
So you're
totally fine.
never gonna give us a 0.
0.
If we guess 0 and it's right, we
might.
get full credit.
If you guess 0 and it's right, you will not get full credit.
Because it won't be right.
We have to show.
Yeah, you have to
You won't be shown your work.
Okay, so number 7. Let's take a look at that one.
Too much.
Number 7.
Yeah, why are we doing number 7?
Does somebody ask? Oh, that's let's not do that.
We have formulas, but.
Unless somebody wants
But if
to.
you don't figure it
We can't use them.
Number 8.
Oh, this was a great one.
I think I put 0 in for this one and it was
Yeah,
right.
me too.
Yeah,
Just
same.
good to go. I went back and looked
And
at
then
it.
my dad yelled at me and I was like,
Oh yeah, this one was 0.
yeah.
Yeah, no, I did that.
I definitely put it 0.
So we
and my
can
mom
use
and
either
I
side.
Okay, so first off, this says use Stokes' theorem to find the circulation of the following vector field around any simple closed smooth curve.
Meaning use the line integral.
So, using the line integral, what would happen? Or there's a couple of things. If we know that the curl was 0, then we would get an answer of 0. Right? So that's one possibility. The other possibility is to do the line integral directly. But let's go ahead and find the curl. So the curl of f. So first off, what is f? Let's write f out explicitly.
Is that 5? No.
F is,
The del.
say that again?
Del phi.
No.
That's another way to think about it, actually.
Phi?
Yeah.
This is phi in here,
Oh, yeah.
right?
That's right.
Yes.
Yes.
Do you agree?
Yes, I knew that.
So f is the gradient of this function. So this implies that phi is equal to 2x sine of y e to the 3z. Actually, that's probably even a simpler way to think about it. As long as we have a conservative vector field, what's true for the path around what's true about the integral around a closed path?
0.
That would be 0. If it's a conservative vector field. Is this vector field conservative?
I don't know.
I don't think
I don't
so.
think so.
Well, like, can
Oh,
you
wait.
just look at it? So
Yes, I do
But
think
is that
so because I know the answer is 0.
We know it was 0.
Wait,
but-
what? Raylan? Jalen? My niece is Raylan. I always want to say
The curl is 0, so.
curl is 0, so that's one way to find it. But is this a conservative vector
Well, if
field?
the curl's 0,
Yes,
then
it's phi.
Why is it a conservative vector
Oh, because
field?
there's a phi.
It is phi.
Because of the way we created it. A vector field is conservative if it has a
Potential
function
function.
Oh.
that has gradient equal to that vector field.
So it can have.
So we are saying explicitly that our vector field is the gradient of this function.
So therefore.
Well,
it's
that means the function has to be phi.
Ah.
So that means that, so f, let's say this, so f is a conservative vector field. And if we have a conservative vector field, we integrate around a closed path, we are going to get 0. So with the circulation integral, with FDR.
So can you stop there?
Yeah, we can stop there. So this implies that closed path integrals are 0.
So pretty much,
So it's all about that last one.
so pretty much we have phi. So they gave us phi already. So that means f is conservative.
Yeah, so we would do phi of b minus phi of a. But in this case, a and b are the same. So the start point and the finish point are actually the same. So we would get 0.
Because
Because it's a closed path.
So it's all about understanding that.
It's all about understanding that concept. So you could also find the curl of this and you'll get that the curl is 0. Let's see, that's going to be a lot more work though.
So if we were to get a problem like this, say on the test, and we wrote that exact thing, is that full credit, 100%, 5 points, everybody's good?
100%.
lot of different ways to say good job. You did it right.
Yes, yeah, totally.
Yes, yeah, totally.
Yes, yeah. Totally.
Why do I sense a hint of sarcasm in your voice?
Because I'm not going to give you something that easy.
You should know this, Omar. You've
Okay,
seen what he's
so number
hard.
9.
Did you take that last exam?
Number 9.
Number 9?
Not that it's on.
This is
Number
also
9.
0.
That's exactly what my mind goes every time.
What?
What is that, like a James Bond thing?
That's a Beatles
Starts
song.
It's a
Number
Beatles
9.
song.
Number 9.
Yep.
Number 9.
Okay, so use Stokes' theorem to find the circulation of the following vector field around any simple closed curve. Now here, they didn't tell us or imply that the field was conservative. So you could test whether this is conservative or not,
Build
which
a
means
phi.
it has no curl. So we're not going to try to build phi unless we know it exists, but they don't even ask us to build phi. So let's just find the curl of this. So let's find the curl. And they're kind of implied, because they haven't given us a curve, they haven't told us what curve to integrate on.
It's probably
That's a real strong indicator, bless you, that the curl is 0. Right.
That they want us to use the double integral side of Stokes' theorem.
That's right.
Aha!
They want that. Because then if the curl is 0, we know.
I have no idea what I'm saying.
What you said is true. There's 2 ways that you could argue the conclusion. If you get the curl to be 0, then that tells you that the surface integral side of Stokes' theorem is 0. Bless you. Or if you say that the field is conservative, you could make the argument that, okay, therefore there is a phi that exists, and because this is a closed path, then we would have the fundamental theorem of line integrals apply, so we'd have phi of a minus phi of a, which is 0. So you can make that argument in either case. So the important thing here really is to be able to make sure that you can find the curl of this vector field. Because the curl of this vector field is going to be, and when we say 0, everyone knows that we mean the 0 vector, right? Not the number 0. Curl is a field. Curl is not a number or a function. It's a vector field. So the only step here is really to double check that we know how to evaluate this.
Would delta sub x, delta sub y, delta sub b, would that be valid syntax for the final?
Totally fine.
Deltas.
Yeah, so if you want to write this, I'll know that you mean the partial with respect to x.
All right, because it's far easier to write, especially since I'm writing a whole bunch.
Totally fine. All right, so partial of this with respect to y. So we're going to get 30x y z squared minus 20 xyz squared. So we're going to get 10 xyz squared. That's not 0. That's not 0.
Stop.
Stop! Partial with respect to y, 30 xyz squared. Partial with respect to z, 30 xyz squared.
Let's get 0.
I panicked.
You're like, no.
It can't be.
Oh, Lord.
So let's check the next one. So with respect to y, we cross out that. Partial of this is going to be 15 y squared z squared minus 15 y squared z squared.
Good.
Good. Z component. Should I write them all down?
No. I didn't mean to have that look on my face.
And then the last one, partial of this with respect to x, we're going to have 30x, with respect to x, 30 yz cubed.
Wouldn't it be 10 yz cubed?
Yeah.
Sorry, 10 yz cubed.
10 yz cubed.
10 yz cubed. 10 yz cubed minus 10 yz cubed. So we get our favorite number.
That is why this
we get 0.
problem is on.
So therefore we get 0. Therefore we get 0.
Also, therefore the field's conservative.
Yep.
Therefore
the field is conservative. Therefore the line integral is 0.
Because you're integrating around this.
Closed path. Yep.
So you're like starting somewhere, but you're also ending there. So that's your
Start and stopping at the same point.
So you're just kind of like, okay. So
Okay, number 10.
Get A from A. Right.
Number 10. Is this a real problem?
This is the one with the A in it, isn't it?
Yeah.
Are there fake problems?
There's some that seem
Which
more.
is this one, 10? Yeah. Oh, I'm 90% sure I redid this one.
There are some that just seem more robust than others.
Robust.
Okay, so we have a paraboloid. A is greater than 0. It's a real number. So there's our vector field for what values of A, if any, does the double integral of the normal component of the curl have its maximum value. So let's take a look at this paraboloid and figure out what our boundary curve is. This is a paraboloid that's opening down with a z value up there at whatever the, if we let x and y both be 0, the z is going to be 49a. So let's go ahead and find our boundary curve. So boundary curve is found by letting z equal 0. And if we let z equal 0, doesn't that mean we can divide by a?
Totally.
Divide by a. So what that tells us is that a does not affect the boundary curve. So this tells us that our boundary curve for every single value of a is a circle of radius 7 centered at the origin. Does not change.
Was that the question? Oh, yes.
Well, yeah, we'll be getting.
That was the question.
That is the question.
So
So there is our boundary curve no matter what. It does not matter what that a value is. So what that tells us is that the line integral is unaffected by that a value, because the line integral says that you're going to integrate FDR on this curve. And so the curve is not going to change given a different a. The vector field certainly doesn't depend on a. Right? The vector field, when we go to evaluate down here, we are going to have f dot r prime dt. And r, the boundary curve, and its derivative do not depend on a. F does not depend on a. So the value of the line integral does not change. If you put in different a's, the boundary curve doesn't change, so the line integral doesn't change. Our conclusion then is that there is no maximum value. The a, it says what value, if any? None. Right? A does not affect the line integral. That make sense?
Wait, so does a in that integral, is that related to the a up there?
This a?
Yeah.
No. These are the standard limits of integration for the parametrization.
In that case, we might want to.
Yeah, so they should use a different letter.
Yeah.
They should use a
Yeah, as my physics teacher continues to complain, variable overuse.
Yeah, we need a bigger alphabet.
You can do alpha and beta in this case.
So what about other ones from 14.7, or are we good with 14.7? Any others from 14.7?
I'm pretty sure there's two parts to that problem.
What's the other part?
I can't remember. I just remember doing it.
So,
I think you have to actually evaluate it.
The surface integral has the same value for all of those.
Oh, just kidding.
Yeah, I think that's it, right? Okay, so let's go to 14.8 and do a couple problems. 14.8. Somebody asked about 5. Is there any before 5? Or
One, I need to read.
what's that?
1 and 3.
1.
Okay, so I got through most of 1, and then like actually getting to integrate it was crazy.
All right, let's take a look at 1. Let's take a look at 1. That seems like a good place to start. Let's take a look. Okay, so it says to use, it says evaluate both integrals of the divergence theorem for the following field and region.
Yeah,
So,
the first one was really easy, and then like doing it with the M dot N was
okay, so first off, is everybody clear that the divergence here is 8?
Yeah.
So the divergence of F,
What number is this?
this is number 1.
14.8, number 1.
Just plug that baby in that triple down there. I like it.
All right. So that is the first part. That was the part you got? Okay, and then, and what was the next part then?
Check for agreement.
Check for agreement with the surface integral?
Yeah.
Just
All right,
says check.
that-
That's the hard one.
Okay. All right, that's
what
actually
you're-
probably more important for us to be able to do, because this is pretty easy.
Yeah, this part was really easy. The first half was easy.
Because that one you can just use volume of sphere.
So we have a sphere of radius 3, and this right here tells us that we have 8 times volume of the sphere. And we know that the volume of a sphere is 4/3 pi times the radius cubed, so 3 cubed. And what does that all give us?
9 times 72.
9 times 32?
Oh, same thing.
282? 2 what?
We just said the same thing but different way.
Oh, okay, so
36 times 8. And
36, oh,
and
36 times
72
8.
times 4 is the same.
Yeah, I was trying to figure out the way that's going to give us the simplest way to evaluate.
Yeah.
So 72 times 4, 288?
Yes.
288 pi? Okay, so that way is the simple way. Now, when we have our sphere, as a solid object as opposed to, excuse me, when we have the sphere just as the sphere as opposed to the solid object, we're just looking at the outside of it, so we have to do the surface integral. So this is the triple integral throughout the whole thing. Generally in math, when we say a ball, we mean that it's solid, and a sphere means it's hollow. So this is with the ball. Now to do it with the sphere, we have to parameterize this sphere. So to parameterize the sphere, our parameterization is going to look like this. And this actually reminds me of something that Saba, you pointed out. One of the problems in our notes from last class, we parameterized the sphere, and then we had to find the normal to that sphere, and we interchanged the u and the v were different.
Oh, I saw that today.
Yeah, they were different for, let me just pull up yesterday's notes real quick.
It's because we used the,
In a previous problem, we had used the u and the v backward, or the other order. Let me just pull this up real quick.
because we made like, switch the u.
So, I forget what page this was on. It's the one where we have negative 4 pi as the answer.
Was it wrong?
No, it's negative 4 pi, but we,
It's 4 pi.
0, 0, 0,
I'm
0.
pretty sure it's negative 4 pi, isn't it?
Oh,
Right. Where is it? Was it the very last one?
Yeah, it might be.
How come I'm not finding it?
It was the column where you used B as C instead.
So what page is it on?
The column, the one you were just on.
No.
That was, I think it was on page 2 of handout 14.7. Number 6.
It's number 6, right. It's 14.7?
Yeah.
So it's right around here somewhere. What the heck? Number 6, where are you? That's the beginning though. Where's 6?
Go to 14.7 notes.
Oh, I'm in 14.8. Dang it. Drat.
Drat.
Oh, it's the F field 0.
There, right here.
Negative x.
Okay.
Y. Yes. No.
So right here, so we got negative 4 pi, that's all right. And then we said, let's do it the other way. And we parameterized the sphere, and we said, oh, let's let v be phi and u be theta. And in a previous problem, we had done the same parameterization. And I said, hey, what was the normal vector from that one? And we just read it off from the previous one. But in that previous one, we had used the u's and the v's in the other order. So what you should do down here, you will get negative 4 pi, but you just have to reverse these two. These two have to be reversed because we switched them in that previous example. We had used theta and phi differently. So if you do this, then you will get the negative 4 pi.
And that only happened because of happy coincidence, right?
No, it was.
No, like the limits where it just worked out and then we still got negative 4 pi. It only happened by coincidence, not the fact that this could happen multiple times, or is that like something?
No, well, if you have the limits reversed the way that, if you have the pi over 2 here and the 2 pi here, you end up with 4 pi when you integrate it. So then something's wrong, and the thing that was wrong is that we had used the u's and the v's differently. So just look at our parameterization. Here we have u as being theta, but here we have v as being theta.
so
Right.
we should have gotten 4 pi? Is that what
You will get 4, no, negative 4 pi is the answer.
Oh, okay.
But if you integrate this with the reversed limits, you end up with a 4 pi and not a negative 4 pi. But if you switch these limits here, you'll end up with a negative 4 pi. So then it will work out how it's supposed to.
Wait, that's for normal vectors or like the?
This is the normal vector to the sphere.
So
the way we find it is do r sub u, r sub v, and cross them. And we didn't go through the whole process again because we had just done it. But in the previous problem where we found the normal to a sphere, we had let v be the theta instead of u. So for this one, just switch those there, and it will work out fine. Or you could just come up here and make all these u's v's or all those v's u's.
So we can always get r prime per phi crossed to r u and r v.
R sub u and r sub v, yeah.
We should have kept the u's and v's consistent.
Yeah, that's, yeah.
So it's just confusing looking back at it now, because all their.
Yeah. Okay, so let's finish up that other one then.
So why is it allowed to write it as curl f dot product n there when the theorem says it's just F dot product N on the last one.
On the one, on what do you mean the last one?
The one that we were just looking at there.
On the old notes?
Oh, that's the old ones. Okay, I thought you were pulling out.
These are the notes from 14.7.
Okay.
And you're saying, and these are.
So I thought you had like suddenly rewritten the divergence theorem using curl.
No. Divergence theorem has no curl.
Okay.
Divergence theorem has no curl. Okay, so we have to parameterize a sphere here, and so that's why it sparked my memory that we had that one complication with the other one. So we're going to parameterize this, and it doesn't matter whether you let u be theta or v be theta. It doesn't matter. It's just, and when you do a problem, you're going to follow it through all the way. You're not going to go back and find the normal vector from somewhere else, like we were just trying to shortcut it there. But in our case here, we'll just go through the standard process. So do you want to let u be theta or u be phi? What do you want? U be phi. Okay. Yes. So 3 is the radius of this sphere. So we're going to do 3 times sine of v. U.
Cosine v.
Cosine v. And then 3 sine u sine v. And then 3 cosine of u. All right, so we're letting v be theta here. So v is going to come from 0 to 2 pi. And we're letting u be phi. 0 to pi.
It's the whole thing?
Yep.
Does it say it's the whole thing?
That's
It's the whole sphere?
that's the parameterization of the entire sphere, yes.
I just don't, what did it say at the top?
Yes, I understand what your question is.
So it must be the whole sphere.
This is the whole sphere, but my question, oh yeah, okay. For a minute there I was thinking, wait, is this parameterizing the whole ball? This is parameterizing just the sphere, just the outside of it, because we're always 3 units from the origin. Right, so it's not throughout the whole sphere. It's not the ball, it's just the shell, it's just the sphere itself. So every ordered triple here is a point on the sphere, not in the sphere.
So if
we're going to have the sphere.
Is that just because there's no like row variable?
Yes, rho is not changing. Rho is constant at 3, so that's what puts us out on the sphere and not like moving throughout.
So we may need to add a W to this to get the ball.
So we need to do what?
Add a W here to get the ball.
Yeah, which we don't want.
We didn't do any of that, did we?
No,
Did I
we
miss
didn't do any of that. And we're not going to. And we're not going to. So now we're going to find R sub u. And R sub u is just the partial with respect to u. There's R sub u. And R sub v. And so again, it doesn't matter which one you let be u and v. You know, if you're going to be going through this, you're going to be fine. So partial with respect to v, then this does not change, and that becomes sine. This becomes cosine, and this is 0. And then we cross them to get our normal. So the normal will be minus 9 sine squared of u cosine of v.
Won't it be positive?
Yes.
It will be positive, yes, thank you. Yeah, because it's 0 minus a negative. Agree. Middle is going to be positive 9 sine u squared sine v. And the last is going to be 3 cosine u sine u. No, 9 cosine u sine u. I'll write it as 9 sine u cosine u. Because we have cosine squared of v plus sine squared of v, so it's just going to end up being the coefficient, which is 9 sine u cosine u.
Wait, so the middle one is not negative?
The middle one is positive because we could either do main diagonal, which is 0, minus the other diagonal, which would give us a negative and then switch the sign, or we could do other diagonal minus the main diagonal.
Okay.
So either way, we'll get positive. So that's our normal vector.
So now we dot that with
Now we are, now we have to dot it. So we're dealing with the divergence theorem, so we just dot it with F, not curl F, just F. So F is our vector field. We have to rewrite the vector field with our parameterization and then dot it with the normal vector. So vector field is 2, 3, 3. So vector field is 2, 3, 3. So it's going to be 6 sine u cosine v, and then 9 sine u sine v, and then 9 cosine of u.
Where did you just give all
From
that?
the original.
Like you just plugged
So
in
we took the field and we plugged in our parameterization.
and you dotted it at the same time.
We haven't dotted yet.
Okay.
Yeah, I was going to forget what everything was, so I just plugged in the vector field there.
Gotcha.
The parameterization. Plugged in the parameterization into the vector field. So now we're going to have the double integral of f dot n ds. So this is over our surface S. And f dot n, hopefully that gives us something with cancellation. So we have 54 sine cubed of u cosine squared of v plus 81 sine, ooh, nice.
How is that nice?
Because this will all combine with the sine squared plus cosine squared.
I know it won't.
It won't?
Because you have different
Oh,
things in
shucks.
Yeah.
In my math line, you have to put it in exactly like
Yeah,
this.
you can't, I was hoping it would combine.
Which
I remember
made
this
me
one.
It
so
won't
sad.
combine.
Yeah.
I was being optimistic. Bad idea.
Bad
idea.
We could always factor out a sine cubed u.
Right, but that's not going to help us
No.
in terms of the integration.
Oh.
Yeah, because their last term doesn't.
Integration
Do we need to
calculator.
write down the integral for sine cubed and cosine cubed? Because those seem to appear quite a bit.
Yeah, will you put that?
Are we gonna need to be able to do this on the test?
Everyone's
In a
just
To
quick
do that?
Sine
The numbers here are a little bit bigger than, I mean, you have to be able to parameterize a sphere.
Yeah.
But perhaps I would give you a unit sphere or a sphere that just doesn't have as many weird coefficients.
Yeah, do we need to be able to like?
And the other thing that's complicated is that the way that vector field is set up is that you get different coefficients, so you can't combine it. So in a test, I would probably give you something where you could combine where these two would be like terms, so that it simplified tremendously. So the question was, do you have to be able to integrate sine cubed? You need to be able to integrate sine cubed.
And cosine cubed.
I'm not, the idea with this theorem is not to be able to evaluate sine cubed. I would not give you a surface integral where there's a sine cubed.
What about sine
A
cubed
sine
cosine?
squared is totally fair.
So what if it's something like on the last exam where we weren't supposed to get a cube, but it's okay with a u sub? Is that something that you might do?
Oh yeah, that's different. That's different.
So
Like
you
if you had a sine cubed of u cosine of u, that's totally different.
Yeah.
Okay.
Right? Because then you just you get a
The
sine
square
of a fourth
messes
of
it
a
up.
Oh,
fourth.
that's
The
fine.
square messes that up.
Yeah, and the v is what really messes it up because they're different letters. So
Oh.
so I won't give you just a straight up sine cubed where you'd have to, how do you do sine cubed?
You don't.
It's
You could
sine.
split it. You could
One
split it into
third.
1 minus cosine squared.
Yeah, because
And
it's
then
an
you
odd
use
power.
something.
So if you remember from Calc 2, if you have an odd power, you pull one off and turn the others to the cofunction.
And then you do u sub.
So I would not give that to
Okay.
you. Won't give that to you.
No parts.
Oh, I remember that.
Yeah, it's really pleasant.
It's really pleasant.
Really pleasant. Whoops. Really pleasant.
So I have a question. This may be dumb, but
There we go.
why are we doing a double integral when in the question it wants a triple integral?
So divergence theorem has two sides. One side has a triple, one side has a double.
Right.
We already did the triple. Right, the triple is this is the triple, we already did that. So the triple is this one right there.
That's the answer for the triple? Or
Yes.
that's- What's, okay, what's the function for the triple then?
The 8, which is the divergence of the vector field.
Oh, duh, there are two options, I didn't think it was.
Yeah, so that's the easy side. And then this is the hard side, so we won't continue on here, but you'll end up with the same answer. And I won't give you a sign cue. Oh, they don't make you go on?
Well, then after this, they just say,
Yeah.
you can just pick the option where it's like, these are,
Okay, equal?
these are the same thing, and then you
Okay.
just put in that answer again.
Right.
The, whatever you got for the volume.
So what do we get,
Of the sphere.
288
Yeah.
pi?
And then you just say, I got that, and you don't evaluate it, because that would be,
Yeah, that's a heinous integral. You will not have to do that.
and you just assume.
Yeah, question?
So Stokes' theorem does line integrals, and then the divergence theorem does area integrals?
No. Stokes' theorem does a surface integral and a line integral. Is that what you said?
I know, I'm just trying to...
So Stokes' theorem, you have a surface that's not closed. The surface has to have some sort of boundary. So it could be the cap of a sphere, it could be a paraboloid that's chopped off. Stokes' theorem is a surface, can't be turned into a solid object. Divergence theorem is a solid object. Stokes' theorem is a surface with a boundary, and divergence theorem is a solid object, and you're doing a triple integral through the inside or a surface integral on the outside.
Okay.
Make sense?
I think so.
All right. Oh, it's time for a break.
That was fast.
That feels so fast. Normally. Okay, so 14.8 number 4. Use the divergence theorem to compute the outward flux across the surface. Surface is the paraboloid for z greater than or equal to 0. And the base is in the xy plane. So divergence of this vector field is equal to
3 or 5.
Yeah, so we just do 4 plus 3 minus 2, so we get 5. So this will actually be kind of a review of some of the stuff that we did on was it the last test? I think it might have been the last test. So we're going to be doing a triple integral multiplied by 5. And the triple integral, let's use a d for the solid objects? D. Yeah. So we need to basically find the volume of that paraboloid. So here we don't have a shortcut. We don't have a geometric formula for the volume of a paraboloid. So what we'll have to do is the stuff that we did in the previous test. Now, do you want to treat this as a surface with vertical surfaces, or this direction, that direction? Upper and lower, front and back, left and right?
Upper and lower.
Upper and lower, of course. Yes. Doing it any other way would be very complicated.
Solve for z.
And then we'll do dy dx. And so z is 0 for the lower surface and 4 minus x squared minus y squared for the upper surface. And then we have the y's and the x's. We have to go look in the xy plane for this. So the projection into the xy plane is a circle of radius 2. So the projection into the xy plane gives us this as our domain. And radius 2. So if we do it the way I said here, we would go -2 to 2 for the x's. And we probably want to change the polar, right?
Oh, that's what I was going to ask.
Yeah, probably change the polar. We'll change the polar, but we'll write it out in rectangular just as practice. So we are using a vertical element then. If we don't use any symmetry, let's just write it all out just for practice. So that circle right there has an equation, x squared plus y squared is equal to 4. So y is going to be plus or minus the square root of 4 minus x squared. So that vertical element is going from the lower semi to the upper semi. So we have minus square root down here and positive square root up here. So that's what we get if we wrote it all out in Cartesian, in rectangular. So clearly it makes more sense to convert those outer two integrals to polar. So using cylindrical coordinates. Probably going to be a little bit easier to evaluate. So we will set this up then as 0, and let's get rid of the inner integral because that's just going to collapse down. So that's going to be 4 minus r squared. Right. that minus that. And we're switching now to cylindrical, so we're going to have an r dr d theta. And r is going to go from 0 to 2, and theta will go from 0 to 2 pi. So there's our setup. Certainly could evaluate it all the way out with rectangular if you want, but polar is more fun.
Do we have a sphere?
We have a sphere?
Couldn't we have just done?
No, we have a paraboloid.
Okay, never mind.
Paraboloid.
I forgot what we were doing.
Yeah, paraboloid. That's why there's no shortcut.
That's why I was.
Right? There's no shortcut. It's not a. We don't have a geometric formula to shortcut the volume of that paraboloid.
But we can shortcut by dropping that 2 pi and make it 10 pi.
Yep. Yep. That for sure. And was there, okay, and this was number 4, I believe, so let's go to number 5. So this says use the divergence theorem to compute the net outward flux of the vector field across the boundary of D, where D is the spheres. Okay. Now, this one, so the divergence theorem has a triple integral side and a double integral side. The triple integral side is going to be a little easier to manage. The double integral side would be very hard because we have a sphere of radius 1 and a sphere of radius 2, and we're trying to find the outward flux. So the sphere of radius 1, we'd have to parameterize it and then find the flux that's going into the sphere of radius 1, because our solid object is, it's like a hollowed out ball. The middle of the ball is missing. So that would have 2 surfaces as the boundaries. It'd have the outer surface, so we'd have a normal vector pointing out, but that the inner boundary, the normal vector would be pointing in to get net outward flux. It's going to be very complicated if we do it with the surfaces, the double integral. So we want to do the triple integral, so let's do that first. So the divergence of our vector field, pretty simple, same story, minus 5, minus 4, plus 6. So we get negative 3. And the triple integral of our solid object, and our solid object is the, it's the chord out solid, the chord out ball.
Oh, so the outside one is.
Yeah. So in terms of geometry, we're going to have negative 3 multiplied by volume of big sphere minus the volume of the small sphere. Everyone follow that? So it's kind of like the annulus type of setup.
Would we be able to just write this out in spherical coordinates just for practice? Again, I've been fine. I've been getting a little rusty on that.
The parametrization in those spheres?
Yeah, in spherical coordinates.
The parametrize of the double integral, or you mean for the boundaries of the triple?
Yeah, the triple integral.
The boundaries of the triple? Yeah, we can do that. So, all right, any question on this geometry piece first? So let's just calculate, finish this off with the geometry piece, then we can set it up with the triple integral using spherical. So the volume of the big one is 4/3 pi r cubed, and the outside one I think had a radius of 2. And then the inside one had a radius of 1. So we end up with 4 pi over 3 multiplied by negative 21. So we get negative 28 pi.
Where does that negative 3 on the outside come into play?
That came from our divergence.
No, but wouldn't that cancel out when we just have 4 pi?
Well, when we combine these things, however you want to combine them, you combine these things, and then you have to multiply by negative 3. I just factored out the 4 pi over 3 to the front, and then I'd have 8 minus 1, which is 7, and 7 times negative 3 is negative 21. Okay, so that is using the divergence theorem, using geometry, and if we wanted to set it up like Will suggested, if we wanted to, if we didn't know the volume of a sphere, say, then we have the negative 3. We can pull that to the front, though. Let's pull the negative 3 to the front. Okay, so we have to find the volume of our cored out ball. So we're going to have rho squared sine phi d rho d phi d theta. Theta is going to go 0 to 2 pi. Phi is going to go 0 to pi. Rho is going to go from 1 to 2. Good. Yep. So that's going to give us the same answer. Yep.
Is it just phi is pi because it's both of like the whole circles, and that 1 and 2 is going to go from 1 to the outside?
So phi has to go 0 to pi because we have to get the entire inner sphere and the entire outer sphere.
But your inside limits of 1 and 2 are getting both of them.
Yep.
Okay.
Yep. Because we're going, so our element, if you visualize the spherical, the radial element, you're coming out with dots, and then you hit the first sphere, and then your element is between the inner sphere and the outer sphere, so rho equals 2 and rho equals 1. So we're only going to count the stuff that's between rho equals 1 and rho equals 2. And this should give us the exact same answer. So 2 pi, there's no thetas, nor will there be any, so we can get negative 6 pi. And then 0 to pi. Rho cubed over 3. Rho cubed over 3, so we're going to have 8/3 minus 1/3, which will be 7/3. Sine phi d phi. And let's see, hopefully we get the same thing. Minus 42 pi over 3. We integrate and we get negative cosine of phi from 0 to pi. Becomes positive 42 pi over 3 multiplied by, okay, that minus is now gone. Cosine of pi, negative 1, minus cosine of 0, which is 1. That's not the same answer yet, is it? Or is it? Hopefully it will be. Is it the same answer?
No.
That's 84 pi divided by 3 with a negative. 28 times 3 is 60 plus 24.
Bingo.
Ah.
Bingo. All right.
Nice.
Better be the same. All right. So that's how you do it using spherical coordinates. I agree. Okay, other one that we want to look at, or do we want to go to previous tests and look at something?
Can I look at exam 3? Like
Exam
something-
3?
We do the switching limits ones. That one, yeah. Not the, is that not the density, but the, you know, the just switching.
So where we have the solid and we interchange limits?
Yes.
There is one of those on the exam. So this is a great one to do. There is one. There is
Because
one.
it's the one that I. Yeah, that one.
Okay, so this one on the test was a paraboloid. Should we modify it a little bit, or just do the exact version?
Let's modify it.
Modify it
the way it
since-
is on the
Well,
file.
are you doing a
Can't remember that.
Are you doing a paraboloid and changing the numbers, or are you doing a completely different shape and changing the one?
Well, it could be a paraboloid that's opening in a slightly different direction.
Okay.
So this paraboloid opened in the y direction. So what if we do a paraboloid that opens upside down? So let's do this. So let's do the z. So let's go from 0 to 4 minus x squared minus y squared. So right now, whenever you see a triple, look on the inside for the surfaces. So right now in your head, you should be thinking z equals 0, the xy plane, and the upper surface is 4 minus x squared minus y squared. That's a paraboloid opening down. So at this point, you're thinking of a full paraboloid. And then we have to go down to the dy dx part. And this is what's going to determine if we really get the full paraboloid or just something in octant 1. And so if I say 0 to 2 and 0 to square root of 4 minus x squared, let's see what we get. So we're going to have our our coordinate system, and we are going to discern what happens. All right, so z is going 0 to 4 minus r squared. There. It's going to be opening down. It's definitely going to come. Let's take a look at the intersection with the xy plane. So if you let z equal, if you set this z equal 4 minus x squared minus y squared, if you set z to 0, we get a circle of radius 2 centered at the origin. So we get x squared plus y squared is equal to 4. So we know down in the xy plane we have a circle of radius 2. And then again, the question is, well, are we going to get the full disk radius 2, or are we going to get part of it? So if we look at the y limits and the x limits, x is only going 0 to 2, so we're not getting the back half. We're only getting the front half, but we're not getting the full front half because this is just going from 0. So this tells us that we're only going to get the part of this paraboloid that is in octant 1. So only in octant 1.
Wait, why is that again?
Because of the zeros on the bottom.
Okay.
Because of the zeros. So if we wanted, if we let this go from negative square root of 4 minus x squared to positive square root, then we'd get the whole front half. Okay? If we change this from negative 2 to positive 2, then we get the entire thing.
We get the whole hemi.
The whole hemi. If we let this be negative 2 and this be 0, what do we get?
The whole
back half.
The whole, yeah, the whole right half. The whole right half. If this goes negative 2 to 2 for the x's, then we're partially into the board, so we're just getting the right half of it. If this is 0 to 2 and this is 0 to that, then we're only going to get what's in the front right corner, just the first octave. Okay, so now let's convert to different order of integration. So let's do that. Let's just put this in. Okay, so different order of integration. Let's go with dy dz dx. So now we know that our surface equation, there's our surface, z equals 4 minus x squared minus y squared. So that's our surface written with z as the dependent variable. Now, if y is on the inside, that tells us that we want to write y, the surface, we want to write it with y as the dependent variable. So all we do is go to this equation, and we rewrite it like that. And then we take the square root, and we get plus or minus the square root of all of this business. But we want the right side, so we choose the positive square root. So that's going to be this limit right here. So positive square root of 4 minus x squared minus z. Is that good for everybody? So that's the right half. Yep.
So that's always how it is with these, is because I think I was getting really tripped up between like, okay, so what do I solve for my surface? So it's always going to be like what we're given, z equals 4 minus x squared minus y squared. That's what we want to use for our inside surface limit.
No matter what. So if y is on the inside, so this is just one way you could write the equation for this surface. You could solve with y on the left, you could solve with x on the left, and so whatever the inner variable is here, that tells you what letter you want as the dependent variable over there.
And then the rest of it's the domain.
The rest of it's domain. So what plane is the domain in for this version?
XZ plane.
XZ plane. So we look to the left. The XZ plane. So our domain is now over here. So the domain for this second integral is this over here. And in that domain, you have a choice, vertical element or horizontal element.
Vertical.
The way I've drawn it is vertical element. So we would put a vertical element inside over here. Certainly the x's are still coming 0 to 2. Those are the easy ones. And now the y's are coming from,
Z's.
or excuse me, the z's are coming from
0 to 4 minus x squared.
So 0 up to this curve. This curve is in the xz plane, so what are the y values for that curve?
0.
Y values are 0, so that's z equals 4 minus x squared. So that's 4 minus x squared.
So you let y equal 0.
So whatever plane is acting like your domain, you let that axis, you let whatever axis variable be 0 that you have to. So in the xz plane, you let y be 0. In the yz plane, you let x be 0. So if we want the equation, so right now I'm pointing, this surface is, right, this arrow is pointing to the surface. If we wanted to just tag that curve in the yz plane, that equation, so this parabola right here, just that is going to be z equals
Just that curve?
4 minus y squared.
4 minus y squared. Because we'll let x be 0 if we're in the yz plane. So that would be just that back parabola. All right, so that's good. So now let's switch and put x on the inside. So let's go with x on the inside. So we're going to have our triple integral dx. And let's see, let's go dx, dy, dz. So x is on the inside. That means x's are the surface. So x is the dependent variable for the surface. So what's x going to equal?
The square root of 4 minus y squared minus z squared.
Minus z.
Minus z.
Minus z.
'Cause
So square root of 4 minus y squared minus z. Is everyone clear on how we got that? We just took our surface equation and we solved it for x. And we're choosing the positive square root, which gives us the front. Now we have y's and z's, so we go to the yz plane, and which direction is the element?
Horizontal.
Horizontal. So now we're going to go this way, right there. So what are the z limits? The constant limits are the easiest ones.
0 to 4.
0 to 4. So we're going to go 0 to 4, and this one is 0 down there. And then the y, go ahead.
Why is it horizontal?
It's horizontal because I have z last.
Okay.
So that means that z has to come from the constant interval, so then it's perpendicular to the interval that's the constant interval. Then the y's are going to come from 0 to
Square root of 4.
to that light blue parabola. So the light blue parabola is this equation. We have to solve that for y. So let's come over here. And that's going to be y squared equals 4 minus z. So y will be plus or minus the square root of 4 minus z. Choose the positive because we're off to the right. So square root of 4 minus z. So that will go right there.
And of these, the easiest would probably be the middle one.
To evaluate?
Yeah.
Yeah, it feels that way because there's no square roots over here, so that would probably, I think that's
But
probably true.
you wouldn't make us evaluate.
No, I'll just have you set it up.
Just like on the.
Yeah, I'll have you set it up just like on the test.
Did you get root 4 minus c again?
That one right there.
So you let x equals 0 in the plane equation?
So we're in the YZ plane analyzing the domain for this surface that's a surface with x as the dependent variable.
Yeah.
So we have to go to the YZ plane. So we're projecting our surface onto the YZ plane. So that means that we're letting x be 0.
And then solving it.
And then in here, we want to know what that curve is, so we have to solve for y. Right?
God, we went over that. It's a good one. And it's
Yeah.
definitely on the exam.
Yeah, there's definitely, I can't believe you asked that, and I can't believe I told you.
I knew it, though.
Yeah, it's a good one. Diana?
So, okay, so on the exam, then it's gonna be one where you're changing and you're not evaluating, but will you have another one where we're changing and we're evaluating?
I don't remember. I don't think I put one of those on there. Because the one we had in the test was kind of goofy, so I just excluded it.
Well, yeah, could we do Lagrange multipliers next example?
Oh, yes.
Sure.
Please.
Yeah, I got
What test is that one on?
exam 2. I got 0 points on it.
All right.
Me
All right, so
Do not run out of time.
another good choice. Wink, wink, nod, nod.
What?
And darn it. So let's do 15.
I also got 0. No, 14.
No, let's do 15.
But that's not.
Hey, whichever one's gonna be the closest to the one
Oh,
on the
let's
test.
do
I'm fine with it.
15.
Or let's do.
Oh, that's the one I actually got right.
This one's good.
So let's not do 14, wink, wink.
Exactly.
Okay.
Oh, good, wait, nice.
So I got
All right.
14 completely wrong next
I'm gonna let's make up a different surface though, different plane, because you already have the answer to that one. So let's suppose.
Don't practice.
So let's suppose we have 3x minus 2y plus 4z equals 12. And we have the point. Let's make the point be 1, 2, 0. Okay, so we've got a plane. Let's make sure that point is not on this plane by some weird coincidence. 3 minus 4.
It's not 12.
It's not 12. Exactly. Exactly. All right. 3 minus 4 is not 12, so we're good. So we want to find the point on this plane that's closest to that point, 1, 2, 0.
I love this one.
So
Yeah, this one was great.
what are we going to do? How are we going to do this using Lagrange multipliers?
We're going to use the distance.
So distance formula. So distance, that's going to be our function.
Yeah, well, I did this one on Monday on the board because I was really stuck on it.
And the distance formula, usually what we do is the distance formula squared as our function. So instead of having that square root, we just get rid of it because this is going to be the same order triple that minimizes distance squared that minimizes distance. So we get that. All right.
So pretty much x minus the x coordinate of the point, y minus y coordinate of the point, and z minus z coordinate of the point.
Yep, so that's our distance formula, the square root of the sum of the squares of the differences. Then we square both sides, and this function here will be minimized at the same order triple as the square root would be minimized.
And this distance function is our f function, right?
This will be our f. Should we call it, let's call it little f.
W.
So then del f is going to be the gradient of that. So partial of this with respect to x. Does everybody see that that's 2x minus 2? Partially with respect to x. Partially with respect to y. We get 2y minus 4. Partially with respect to z. Everyone okay with that? Now we have to take the partial of our constraint. So the constraint is the plane. Distance function is finding you all these millions of distances from that fixed point to the plane. So the plane is the constraint that we want to use. We want to minimize subject to this constraint. So that gradient, this is our constraint. Does he use a capital G?
Yes.
So we'll call that, and maybe he uses a capital F for that.
He uses a W.
A W?
Yeah.
Yes.
Oh. Okay. Whatever. Oh boy.
Whatever.
Whatever.
I think he does.
Whatever the letters are. So this is 3, -2, and 4. So now the way Lagrange multipliers work is the max or min will occur where these two gradients are parallel. So this has to do with contour curves and where they intersect. And all we have to do is set up a little system. So we say, okay, well,
Oh, this is the lambda one.
2x. Yeah, what he says.
The one we had on the test was so nice though because y equaled lambda and that is not going to be the case.
Yeah, I just made this one up out of thin air, so it's going to be a little bit more messy probably. Okay, so we have that, and then our constraint equation is the plane, 3x minus 2y.
Okay, that's convenient.
Yeah.
You actually did pretty well.
Did I get lucky?
Yeah.
Okay, so we can solve each of these for x, y, and z, plug them into here, find lambda, plug lambda back in, and boom, we get our x, y, z.
Boom.
So let's do it. Yahtzee. So this tells us that this tells us that x is equal to, where does it? So 3 lambda plus 2 divided by 2.
You can take lambda directly from the z equation.
Yeah.
Oh, that's true too.
But you still have to solve for x, y, and z.
Yeah, we still have to solve for x, y, and z. That's true.
Plug it into
So I think this method here is going to
Right, so we
be
take it
probably,
and then we're gonna
oh,
plug
2y. Let's actually take out the
lambda,
2.
and then we plug lambda back into here to get our x, y, and z's. Figuring this out, I'm pretty excited.
And then this one is the simple one, like you just said. We don't even have to do anything. Let's just leave it as 2z. So let's plug in then to our constraint equation. And plugging into our constraint equation is going to give us a whole bunch of
Nice
nice stuff. So that minus 2y, so that's going to be plus 2 lambda minus 4. Plus 4z, we just double that, so that's plus 8 lambda. Equals 12.
I like this.
And then we can, let's multiply everything by 2 to get rid of this fraction here. So we're going to have 9 lambda plus 6 plus 20 lambda equals 32. There's no way that's going to be divisible by 29, though, is there? So lambda will be 26 over 29.
Yeah.
So what you guys got?
Wait, are you doing this? Your numbers aren't the same as the exam numbers.
No, that's what I said.
Okay.
Yeah.
Then someone else is doing it. I thought you were like asking if we got the same.
No, not on the exam.
Okay.
Is that 2 lambda near the top actually negative?
Right here?
Yeah.
Let's check. So we have 2y is equal to that.
Well, then how is...
So minus 2y would be minus there and minus there. So
I accidentally had that as a positive 2 up at the top.
So I think that's right. Grant?
I'm good.
I'm good.
So, so 9 lambda plus 6, then that's 10. We doubled, so we get 20. That's 16. We doubled, we got 32. That's good. So then our ordered triple, we come, what did we get? 26 over 29.
I have a question.
Yes.
Where'd your over 2 go right there?
I doubled it. So I multiplied both sides by 2.
Oh.
So instead of just a 10 lambda, I made it a 20 lambda.
Gotcha.
Instead of 16, I made it
Just to
32.
make it easy.
Just to get rid of the fractions.
Wait, where the
Nice.
hell did 16 come from? Oh, you subtract the 4 over. Duh.
Add the 4 over, yep.
Math, words, stuffs.
Oh boy.
We're doing great this year.
All right, so then I think everybody knows then how to find the x, y, and the z.
Yes.
Plug the lambda in there, plug the lambda in there, plug the lambda in there, solve for z.
Nice.
All right,
You have a nice ordered triple.
not too bad. So that's a reasonable type of one for the test. There's not a crazy system that you get tangled up trying to, oh, if x is 0, then do this. If x is 5, then do this.
That x, y, z we find is then just that point that is closest on the surface.
Right.
Okay.
So let's think conceptually about that for a minute, because the Lagrange multiplier method finds maxes and mins. And so the question will be, well, this ordered triple that we found, is it a max? Is it representing the point closest to that or the point furthest from it? And what do we know about a point in a plane? There is no point on the plane that's furthest from a given point, so it can't be a max. So that point has to be, by process of elimination, it's got to be the minimum point.
So you
The
can
point
never,
with minimum distance.
you can never get a maximum Lagrange multiplier in a plane.
Not for the distance from a point to a plane, no. Now you could get it for some other geometric object.
Like a sphere?
Like a solid, like a sphere, yep. Yep.
Could you just scroll down really fast?
Yes.
I have a question.
Yeah.
When you multiplied everything by 2,
Mm-hmm.
Did you really multiply everything by 2?
I don't think so.
Yes.
No, the 4 didn't get multiplied. Oh, no, the 4 got.
So this guy right here, the 2 goes away, so that becomes 9 and 6. Up here we have 10 lambda, but if we double it, we get 20. Up here we have 16. If we double it, we get 32.
You obviously should not have skipped that step. Since everybody's confused.
Skip the multiplication by 2 steps. Do you agree with it?
I don't see where 2 minus 4 becomes positive 6.
But there's a lambda there.
So when we multiply by 2, this becomes 4, this becomes 16. 16 plus 4 is 20.
Yeah, I got that.
This becomes -8, this becomes 24.
But what about that positive 2 on the top?
This one?
Yeah.
Well, multiplying by 2
That's
takes
2,
this
right?
2 away.
But wouldn't that be a negative 6? Positive 2 and negative 8?
Oh, wait, what? when we multiply this term by 2, the 2 just goes away, so
Yeah.
we have 9 lambda plus 6.
Plus 2.
Plus 3 times 2 is 6.
Oh, I got it. I
Okay.
got it.
Thank you, Grant. Will?
Yeah, so has anyone else solved it yet?
Which one?
This one.
This one.
Oh, so you get the actual numbers? Does somebody have an X?
Yeah, I have them 68 over 29 by 32 over 29 by 52 over 29.
You're saying it like you see that.
Right to me.
So we'll assume that
Yeah.
you subtracted and added properly.
I know if this were yesterday, I would have said no, but I think I'm.
Till you feel more confident?
Yeah, I was having a lot of calculator issues on Monday.
Calculations.
I got
Sometimes you.
139 over 52 for X.
Uh-oh.
Oh dear.
Contradiction.
You can divide that by.
We do.
I don't think you should have it over 52.
Yeah, I agree. Everybody
Okay, so
agree.
another test question.
Yeah.
Can we work on some of the
49, yeah.
finding limits?
Finding limits for what test?
From exam 2, 5, and 6.
see this.
I had
Exam-
some problems on some of those.
Exam 2, 5, and 6.
Yes.
Alright.
Yeah.
Exam 2.
I had some problems with, I think.
Okay, so, alright, yeah, let's.
Oh,
I figured them out now.
Limits. Which one would you rather look at?
6.
The one that's wink wink.
I can't remember about the limits one.
Is there a limits one?
I can't remember.
68 over 29.
Go look right
I
now.
can't remember. I honestly can't remember.
6.
Okay, so 6.
I 6 out.
6 is one where there's a couple of choices. So there's a couple of choices. You can go to polar if the x and y are going to 0, 0. That's the only time you can go to polar. So if you look at number 5, the limit is not at the origin.
No.
So you cannot go to polar there. On number 6, you can go to polar.
No, it's 29 equals 26 lambda.
So let's do a polar. Let's do one of these. Maybe we'll do one of each.
Can we go back for a second?
We have a feud here.
To what?
Scroll to the bottom. I obviously saw that wrong. That explains a lot.
Explains a lot.
Carry on.
Wayward students.
Know it.
All right, so let's do one of the 6 ones. Let's do part A.
Oh, is this, okay. Two-way testing? Two-way?
This one.
See what's polar.
Okay, so this says show that the limits do not exist. Show the limits do not exist. So you have a couple of choices. You could go to polar and show that you don't get a unique value, so the limit does not exist. For a limit to exist, you have to get a single number. Or you could try 2 paths to show that the limit doesn't exist. So there's many ways you can go. So let's take, changing this to polar is a little bit messy just because it's not an x squared plus y squared. It's not quite as clean, but it would still work. Let's try the path method first. So let's say along x equals 0. So a limit does not exist if 2 paths have different limits. So if we go along x equals 0, then we're going to take the limit as y goes to 0 of this. And what's that limit equal to?
1.
-1. And the standard places to check are along the axes first. So if we go along y equals 0, we're going to take the limit as x goes to 0 of x cubed divided by x. And what is that limit?
0.
Everyone agree that it's 0? Crystal clear? So these are not equal. Therefore, D and E.
So we only need to do 2. If we get 2 different,
Yep.
we don't need to.
The only yeah, then you're lucky. Right.
And then
Then you're lucky.
I didn't get lucky on either of them. I had to do 3.
Yeah, so if you don't get lucky, try third. So any issues on that? How about number 5?
let's do that.
Let's do one of those. So A or B?
Let's do the first one.
To point out, both of these are in the lecture.
The one where we can do polar.
Exactly, both of them. They're like listed.
What was that?
Can we do polar on either of these?
Oh, do
A.
you? So am I hearing that you want to do B and 5?
Oh, I don't care.
I don't know.
Sean, is that what you're saying?
Either one works.
Okay, so B for 5. So 5B, we have limit. So this reminds me of a college algebra problem.
Yeah, that's what I was going to say.
This is a lot like,
Are we going to do this in the hospital?
I don't know. Let's see what happens. So when you plug in your 0 and your 1, you get 0 over 0. It doesn't work. And in college algebra, you had a bunch of these, which were kind of counterintuitive because you had to rationalize the numerator instead of the denominator, which just feels weird because you were always told rationalize the denominators. So you have to rationalize the numerator here. So you multiply by the conjugate, top and bottom. Multiply it out, and let's see what happens. So we still have limit. And in the top, when we multiply that out, we get x plus y minus 1. And in the denominator, you don't distribute, you just rewrite it. And then the numerator and the denominator have a shared factor. So this is going to turn into just the limit of 1 divided by square root of x plus y plus 1. Because these are a common factor. Now we plug in our 0 and 1 again. We plug in our 0 for x and our 1 for y, and we get 1/2. Seems so easy now.
Look at my work.
It's like, how did I miss that?
I don't even know what I did.
You.
She went like,
Yeah, right?
I only took off 2.
over
Someone said something about the L'Hopital's rule right
Yep.
before. Isn't there something like we can't use that?
When there's 2 letters, you can't use it.
Okay, that's not.
So as soon as we, like on this one, as soon as you get rid of one of the variables,
Okay,
then you could use L'Hopital's for either of those. But
Okay.
you can't use it if there's an R in a thing.
That's what L'Hopital's is.
Say again?
Take the derivative.
Yes.
On top and bottom.
Derivative top and bottom.
Okay.
So you can't do that if there's 2 variables.
Okay.
But once you've reduced it to 1, you can do it. All right, other ones?
You said that was 5B. What is that? What is that 5B of?
Exam 2.
Exam 2.
Okay.
Yeah, so these are off exam 2.
Oh, that looks like a 4.
Is there a...
We haven't had exam 4 yet.
if we get one of these.
I thought you were just being really nice, honestly.
Right?
Literally just to the bottom.
Exam 4. Omar?
Is there a multivariable L'Hopital's rule?
No.
Ever?
Nope. Diana?
Can we just go over number 8 on exam 2? We don't have to work it all out, but I got.
Yeah, there's no analog to L'Hopital with
Sorry, it's going to be the
multivariables.
hospital.
8 is the cent will change.
Oh, yeah.
Just despite L'Hopital.
All right.
And also it may turn out that you're doing a problem that uses the rule may put you in the hospital.
Exactly. When did you do this? Oh, when I was in the mental asylum, which is called the hospital.
Yeah.
So this is on exam 2 also, number 8. Exam 2, number 8. and find unit vectors that give the direction of steepest ascent and steepest descent at that point. Okay.
Is this
Example number 8.
directional derivative?
Directional derivative stuff. Okay, so steepest ascent and steepest descent is, how do we find that?
Gradient.
Gradient. So the gradient of our function is the vector of partial derivatives. So this is going to be, partial with respect to x is going to be 8x cubed minus y. Partial with respect to y is minus x plus 2y. All right. So then what do we do with our gradient?
Find the gradient at the point given.
So we want to find the gradient at whatever point we're interested in. So
It was 1, -1 on
so in this case, it's 1, -1. So the gradient at this point is going to be plugging in x. So 8 plus 1 is 9.
-3.
9, -3. All right. So,
Exciting stuff.
so what is the direction of maximum increase?
Unit vector.
So it's 3 root 10.
So we want to figure out, typically we ask for unit vectors, the unit vector in the direction of maximum increase. So we find the length of our gradient, the magnitude of this gradient is going to be equal to the square root of 81 plus 9 squared to 90, which is 3 root 10. And so the unit vector that points in the maximum direction is just the gradient divided by that. So we're going to have 3 divided by root 10, comma, -1 over root 10. And then we could rationalize the denominator if we want. So u in the max direction, and what would be the unit vector in the min direction?
Would it be pretty much -1 over root 10 and -3 over root 10?
Just multiply by -1.
Easier than that. We just change the signs. Right, so it's the classic thing if you're standing on the side of a hill and you're looking up at the steepest side, in the steepest direction, turn around 180 degrees and you're looking in the path as fast as the quick way down. The quick way. Fast up, fast down. No, slow up, fast down.
Hopefully the safe way.
Best sled
Safe
in the
way.
area. The best place to sled. The best direction
Yes,
to
the
sled.
fall line. Best place to ride.
Oh, I thought that'd be like the jump off.
What about
and
no change?
Yeah.
Paradise.
Okay, so what about no change?
Because it might be
I know you
cliffs,
swap them,
so
but
you
why
jump
do you
off
swap
and
them?
So
steepest
the
descent.
gradient is giving you the direction of maximum increase, and the gradient is orthogonal to level curves. Level curves are curves of constant function value. So if we just imagine, so if we imagine a level curve, let's just think about a level curve right there. That's a level. Suppose that's a level curve. If the gradient is pointing perpendicular, that means that in the direction of the level curve, so parallel to the level curve, that is going to be the direction of no change. Because that's what a level curve is. It's a curve of constant function value.
Oh, I get it. So to make it the dot product 0.
Yes,
Okay.
exactly. So we want to make the dot product 0, so the u in the no change direction, no change, we swap them and change one sign. And there's two answers here, right?
Yeah.
You could swap them and change the x or swap them and change the y, it doesn't matter. So that is a unit vector pointing in the direction of no change.
Going to the steepest ascent and descent.
Yep.
So when you find like the first one, is that always going to be the steepest ascent?
Yep. So the gradient will always point in the direction of steepest descent.
Okay.
And then multiply by -1 to get the direction for steepest descent. Exactly.
Do we have another wink wink problem you may know off the top of your head?
Give us a good one.
Yeah, I should have brought that test with me.
Why don't you go get it?
Why not go get it?
I can go get it.
Yeah, I didn't get enough. I'm not falling for this shenanigans.
It's barely over 10 minutes.
All right, so another question?
Oh, can we do number 9 on exam 3?
Number 9, exam 3.
Yeah.
Yeah,
good job.
Set up and evaluate a triple integral to find the volume of the solid bounded by some stuff. Okay, bounded by stuff. Bounded by stuff.
I was like, on JK.
I'd like to see, I'd like you try to use that in the final exam. We got interesting.
It's all bounded by stuff. It feels like we're math orders. Bounded by stuff. All right, so number 9.
Number 9.
Number 9.
Is this the second time problem number 9 has come up?
Yeah, I think so.
Yeah, unfortunately.
It's a special problem, number 9.
Well, I got the test credit wrong on this one too.
Okay. So we have coordinate planes and these surfaces. So the coordinate planes, we have x equals 0, y equals 0, and z equals 0. Okay, do you first see that that function right there is a cylinder? So we've got to be really clear. A lot of times when you build these wedges and things that are wedge-like, you're dealing with cylinders many times. So there's no y there, so you know you're dealing with a cylinder. So you're pulling in the y direction. This is also, it's a plane, but you can think of it like a cylinder. If you graph this in the YZ plane, then you pull it in the x direction. So let's go ahead and see if we can piece those two together. So z equals 4 minus x squared. That's in the xz plane. Excuse me, yeah, xz plane. XZ plane. So 4 minus x squared, that is a parabola. Oops, I want to put those there. 1, 2, 3, 4. Now, we know that we're bounded into the first octant because of this other stuff. So I'm just going to draw that piece of it. Everyone agree? 4 minus x squared in the z-plane? And then that gets pulled in the y direction. So that's going to get pulled this way. We don't know how far it's going to be pulled yet. So maybe you don't want to connect anything, but if you just sort of want to be visualizing just that one surface, that's what it looks like.
Oh, I remember this one. I drew a nice surface for this one.
Where's my original?
Because there's no y.
Not on my evaluation, but on my drawing.
Yep, no y, pull y.
This one's like
no y is unrestricted. It can be anything.
It's like
pull it in the
one
y
of
direction.
those like wall lights that's like a half tall wall light, but sideways.
So now let's go and look at the second one. So z equals 6 minus y. That's in the yz plane. So we go to the yz plane. Go up to 6. Out here, we'll imagine that this is at 6 right there. So that is just a line with slope -1, and it goes between these two 6's. So it's just coming down like that, right there. And then it's being pulled in the x direction. So we've got that green wedge, and that blue plane is just going to chop off the side. So what we'll do then is go back to the drawing board. Bless you. We will erase this green stuff here because it's going to be chopped off by that. This.
Oh, I should have done that.
And it's coming this way. And so now it's chopping it off, and it's just going to create a slanted side. We can probably get rid of this up here now. Whoa, what's going on? Bless you all. So we're just chopping off this diagonal chunk of our wheat shed cheese wedge. Looks like a cheese wedge. Looks like one of those big, huge Costco chunks of cheese.
I don't think we watch the same or get the same cheese from Costco. I don't think so.
Oh, you get those little squares?
Yeah, I'm about the little squares. The Tillamook squares with variety.
Oh, dude, we can be friends.
All right, so any question on how we get?
I'm a deli boy. I take whatever size cheese I want.
Do you tell them what shape you want?
No, I work in the deli. I can.
Oh, you at Costco?
No, at Safeway. So I can slice all sorts of fun shapes.
Oh, so you should be making us some hyperboloids with.
I'll try. I'll see what I can do.
Took you this long, man.
I didn't know there was a
hyperboloid of 2
Any way you slice it.
That way, stuck together, floating in the air.
Stuck together with some sort of coat hanger.
Oh, it looks like the scoop for a Formula One car. That's what it is.
Ah, yeah, just all.
Do you see that?
Oh yeah.
You see that before you see the cheese?
I saw the cheese first.
Okay, so now can we use a lower and upper surface to find the volume?
No.
No.
Is that totally obvious now?
Very,
A
very,
little
very,
bit.
very.
It's very obvious, right?
What obvious?
You cannot use, there's no unique upper surface. If you're dropping something down, it's going to here has a different upper surface than over here. So you cannot do lower and upper. So I forget how I did it on the keys. We could do left, right, or back, front.
Right, left, right.
Left, right's probably the most intuitive because you can see the right surface, that light blue tilted plane. That's probably the most intuitive. So should we do it that way or should we do it the other way then?
That way.
All right, let's do it that way.
That way.
Because I messed it up and I did it.
All right, let's do
We're doing that.
So triple integral, we're just trying to find volume.
We did the other.
So the inner integral is representing our surfaces. So y equals 0 is the left edge. Y equals. Yeah, so we solve this one. We get 6 minus z. That will be our right edge. So where's our domain? What plane's our domain in?
XZ plane.
XZ plane, exactly. So there's our domain right there in the XZ plane. And you want to do a vertical element or horizontal? Vertical makes way more sense than horizontal. So vertical element right there. So that tells us that the x's are coming from the constant interval
0 to 2.
0 to 2. And then how about the z's? 0 up.
Minus x squared.
Yeah, exactly.
How pretty.
How pretty.
So we don't even need to solve anything, like, it's just z equals 4 minus x squared. We're given that already, so we might as well.
Right, because we were given that cylinder, so we already know what that curve is in the xz plane.
If we did dx dz, it would just be a root.
Yes.
Okay.
So, yeah, so that's a good question. What if we change that to dx dz if we went horizontal? Then we would have to take that and solve for x, and we get x equals 4 minus z square root.
My calculator to
And then z would go from 0 to 4?
Z would go 0 to 4.
Boom.
So if you did do that, let's just write it since we talked about it.
Decompiling.
So
I can code, but I can't uncode.
code, not uncode. So we still have 0 to 6 minus z, 0 to 4, 0 to square root of 4 minus z.
Sounds like hell.
I know Java.
How's that look? Feels a lot easier.
Decompile it.
Now we've been in 3-dimensional space doing all sorts of limits.
I don't know anything about it though.
Right. That's a good sign. It's a good sign. All right, we have just a couple minutes. Is there another one that you want to talk about before we?
Not exactly that.
Are we gonna have to do the AFT and the AFT?
Finding the components of acceleration?
Yes.
I would definitely know how to find the components of acceleration.
As in AFT and
No German, please. Omar?
First of all, what section is that components of acceleration? Because I do not remember.
12.
Is it exam 1?
Or it's like
Exam 1?
it's the u cross product v over v cross product v cross
Is it
product
AFT
v.
and
A sub t and A sub n.
Yeah. That's
So
first
that
exam.
which exam though?
Exam 1.
It's from one.
Exam 1.
Yeah, because we were just learning how to use vectors.
acceleration. That was my second question. Is there any hint for exam 1?
Here's one hint.
Can you like cut a couple of them off, maybe? Or
Here's a hint.
that help?
That wouldn't help too much.
Doing 45 a day is kind of killing my soul.
You have a study guide posted for the final, right?
Oh,
Yeah,
projection of you on
the best way to study for the review stuff, though, is just to go over the old exams. I wouldn't go study a bunch of new stuff.
Definitely
I know
gonna
this.
do that on the exam, but that's my specialty.
So, this. So, question here. Let's suppose this is a point in three-dimensional space, and this is a line, and that line has equation. So the question is, how far away is that line from that point?
Yeah, I think I did this
Perp.
one.
So, what'd you say?
Perp.
P-perp? Exactly. What's the length of P-perp?
U minus P. Which
More?
is,
There's more? You're on the right track. So what is the direction vector? First off, let's get the direction vector for this line.
2, 3, -1.
2, 3, -1 is the direction vector for that line. And let's get this vector here. This point right here, we're going to grab as -1, 1, 0. Right, if I plug in t equals 0, we'll use this as that point right there. So then this vector here is what you were saying. So 4 minus -1, -1, -1, and then that. And then we cross the two to get the area of the implied parallelogram right there. So we're going to do 5, -2, 3, crossed with 2, 3, -1. That gives us 2 minus 9. That gives us 6 minus 5, so 6 plus 5. I think I did that right. 15 plus 1. Is that right?
you go
Yeah, I
a
got
little
6 plus
bit.
5. I got 6 plus 5.
6
See? You can also do it this way. You can do the proj v.
So what is the magnitude of this vector then? That's the area.
Of the parallelogram.
So area of the parallelogram is equal to the square root of the sum of the squares, whatever this is going to be. I can't even think about 19 squared right now. And then how do we find the distance?
So we have to do it
Divide
with
the area by the base.
magnitude.
So if we have the area divided by the base is going to be the length of this vector right there, which is square root of 4 plus 9 plus 1. So that will be our distance.
So you found your u vector by doing what?
So we
Oh,
did the cube.
subtracting.
So whatever those numbers.
That number is 3 root 59
On top?
on top.
I did that right.
Okay,
And I
So everyone clear on how to get these two? Those are probably the most important things. So this 2, 3, -1 is the direction of the line. The -1, 1, 0 is any point on the line. So I plug in point t equals 0. You could plug in another t
and then
value.
you just
T
subtracted
equals
those
0.
to get that vector.
And then we subtract terminal point minus initial point to get displacement vector. Cross those two, find the magnitude, that's the area, divide by the length of the base, and then we get the distance.
If I do it both ways, can I extra?
Maybe.
Okay, I'll do it both ways.
All right, let's go.
Nice.
Bye.
Woo! Good luck studying, guys. See you. Did you say up or down? Down.
You were asking me like this way? No.
Yeah.
Last big study weekend of the semester.
I know in like the 2 dimensions, wasn't there a way to do?
Don't mess it up.